with all the preparations done, we can now conclude the proof that there's 27 lines on a smooth cubic surface. The central ingredient that we are going to use is the result that we have seen last time, namely that this incidence correspondence parameterizing cubic surfaces in lines such that L lies in the cubic surface. Inside this product here is, first of all, it's a Zariski closed subset in the product. And then if you project onto the first factor, just remembering the cubic surface, then M is locally the graph of a differentiable function from some subset here to the Grassmannian G24. Okay, and so you can conclude as a corollary from this that every smooth cubic surface contains exactly 27 lines. And so in this proof, we're going to use this complex or classical topology everywhere, because this locally here is locally in this classical topology, and so we have to use that one. And so let's say we have a fixed cubic surface X. So we fix one point here, and then we start looking at points in the fiber. So we look at lines L, and we actually look at the fiber of this full projection from U cross G24 to U. So we look at any point L in this Grassmannian of lines. And then there's two possible cases. The more interesting one is that this line actually lies in the cubic surface. It's one of the lines that we're interested in. Then, by the result above, we are locally the graph of a function. And so locally in the classical topology, well, the classical topology on this product is the product topology. So we find an open subset in the product topology where we are such a graph. And then we can always restrict to a smaller open subset and find such a kind of square, or such a rectangle or such a product environment. So in other words, we found an open neighborhood VL cross WL of X, L here, such that in there we are, if we intersect M with this neighborhood, then we are the graph of a function, and now this function is defined on this VL, and it goes to this Grassmannian 2,4. And so in particular, what we see that so if we are in this neighborhood VL of X, and we look up and we only look at lines in WL1, so this means we look at things inside this product, then every cubic in VL contains exactly one line contained in this WL. So at least on this small product, everything downstairs has exactly one line there. So this is the interesting case if the line is contained in the cubic surface. The less interesting case, this is this case 2, the line doesn't lie on the incidence correspondence. And so this means we find an open neighborhood, which just doesn't intersect this M. And the reason for this is the kind of first part of the lemma that we showed. This M is a Zariski closed subset of U cross G24. In other words, on some affine open patches, it's cut out by polynomial equations. But I mean, all polynomials are in particular continuous in the classical topology. And so having them vanish is still a closed condition also in the classical topology. So M is also closed in the classical topology. And so if you are at the point not in M, that means you find a small open neighborhood which doesn't intersect M. That's the definition of the complement of M being open. So we find this other open neighborhood, which we also call VL cross WL, such that M just doesn't intersect this thing. Here we use M is closed in there. So these are the two possible cases. Either you're contained in the surface or you're not contained in the surface. And then, well, if we look at this fiber here, so we now look at this full fiber over X. So all possible lines, this is isomorphic to this Grassmannian. And then this Grassmannian here is covered, of course, by the WLs, because WL is always the neighborhood of the L itself in the Grassmannian. And so this Grassmannian has this open cover. And now we use kind of cool property of the Grassmannian, namely, it is compact in the classical topology. Because we have seen the Grassmannian is the Zariski closed subset of some big projective space. So it's also a classically closed subset of this classical projective space with the classical topology. But we have seen that the projective space is compact. And then if you're a closed subset of something compact, you're again compact. Okay, so the Grassmannian is compact and it has this cover by open sets. And so by the definition of being compact, we find the finite subcover. So somehow we find finitely many points in here such that these green boxes cover the entire fiber like this. And then, well, we have the second neighborhoods of X, these VLs. And so if you now intersect all of these finitely many VLs, then you get all the good properties that you like. So somehow on this intersection of all of these things, this is still an open neighborhood of X in U. It's true that any X in this open neighborhood has the same number of lines, because, I mean, then you just count how many lines do we get from case 1 and how many lines do we get from case 2. From case 1, we each get exactly one line in this neighborhood here. And here we get none. So somehow this number of lines is just the number of LJs in this finite cover, which are in the case 1. And this shows us something very nice, namely that the function from U to the natural numbers, which sends any X to the number of lines in X, that this is a locally constant function. Note in particular, I mean, a priori, we didn't even know that there couldn't be an X which has infinitely many lines. But in fact, this argument, since we chose this finite subcover, and in each portion you have at most one line, we know that this is actually well defined. The number of lines is always finite. This we have already shown now. And we can get even better, namely that this number is a locally constant function, because in this neighborhood V of our chosen point X, it is constant. Okay, so we know every smooth cubic surface has a finite number of lines, and this number is a locally constant function on U. And now we just want to conclude. And so to conclude, we see that U, now we want to show U is connected, because if we have connected, this means this locally constant function must actually be constant. And then we have seen the particular Fermat surface has exactly 27 lines. And so then every cubic has to have 27 lines. And so we just have to show U is connected. Now we have actually seen in the Zariski topology, U is even irreducible. But somehow the Zariski topology and the classical topology, comparing them can be a bit difficult. So let's give a separate argument why U is connected in the classical topology. This is actually not super hard. This P19, this is certainly connected. I mean, for example, it has this cover by affine spaces, which are just complex numbers to the 19, and they all intersect, and so you can move from any point to any other point. And we have seen this U is this minus a certain proper Zariski closed subset, namely the subset where the surface defined by this equation is not a nice smooth cubic surface. And so this proper Zariski closed subset has therefore complex codimension at least 1, because it's not everything, it must have codimension at least 1. And so complex codimension at least 1 means real codimension at least 2. And then you can check if you have a real manifold which is connected and you remove something of codimension at least 2, then you can always kind of move around it. I mean, essentially the idea is if you have, for example, a 2-dimensional plane and you remove finitely many points, these have real codimension 2, then it's still connected, because any path that you want to take, even if it went through this point, you could just move it a bit and then it no longer goes through the point. And so you remove something which is just too high codimension, and so this remains connected, and then we're done. So this locally constant function is constant. We have evaluated at one point to be 27, so it's 27 everywhere. So this was the full proof. And you see, I mean, in the proof, we did use some things which we didn't quite define like this. So we waved our hands a bit, but I hope it at least somehow the idea became clear. And we have seen how all the ingredients that we have developed so far came together, this Jacobi criterion and so on. So let's see a couple of remarks about this. If you have taken, for example, an algebraic topology class, then what we have shown here, that this M is locally a graph like this. Actually, you can formulate it as saying that this M to U is a covering map. And then we have just shown that it's actually this finite covering map of degree 27. So it's 27 sheeted covering. Each cubic has exactly 27 lines on it. And then if you remember, we also had these extra characterizations of the lines, namely if X is a cubic surface. In a special example, we have seen that given any line in the cubic surface, there's 10 other lines meeting it and lying in the surface. And giving 2 disjoint lines, there's 5 lines meeting those 2. This we checked for the Fermat cubic. And in fact, this holds for arbitrary smooth cubic surfaces. I guess it should be smooth cubic surface here. And the proof goes by a similar incidence correspondence. So then you have an incidence correspondence of, for example, a smooth cubic surface X, and then lines L1 and L2 inside X meeting at a point. And then you show here the projection map from this, only remembering X, is a 10-sheeted covering. And similarly, you have this here where L1, L2 are disjoint, and L3 meets both of them. And then you have the 5-sheeted covering like this. So very similar proofs show that this pattern still holds true for any smooth cubic surface. And the last thing that I want to say in this video is why are we even counting things in a cubic surface? It seems pretty arbitrary. Why did we choose cubic surface? Why didn't we choose quartic surfaces or quadric surfaces and so on? And now that we have seen the proof, we can actually understand where this cubic surface comes from. So let's say we want to count things in surfaces inside P3, but let's say we allow the degree to vary. What happens for different degrees? Well, we can do one of these things called a dimension count. We can count how many lines are there in general and how many conditions do they have to satisfy to lie in the surface. So if we look, everything is inside P3, then the number of, or somehow the moduli space of lines in there is still the Grassmannian 2, 4, and we have seen this has dimension 4 and local coordinates given by these 4 coordinates here. And then let's say you had a degree D equation in here, then then for the line, so this cuts out some degree D surface inside P3. And then the line lying in the surface means your equation must vanish on this entire line. So in other words, if you plug again our parameterization of the line in, then this here must vanish for all S and T. But you see, this is an equation of degree D, is still degree D in S and T. And so, so this vanishing means if you expand this, then you get a sum over s to the I, t to the d minus I times this big Fi, which we have seen. And then all the big Fi must vanish. And so the total number of these big Fi are d plus 1, namely 1 for each monomial in S and T. And so we have d plus 1 equations in these, if you fix, let's say, if you fix the surface, if you fix the C, then these are still equations in these 4 variables. And now we see there's only one degree d where the number of variables and the numbers of equations match up, namely d equals 3, when we have 4 equations and 4 dimensions of these local coordinates. And so somehow the expectation is if d is less than 3, so for example, if you count lines in a degree 2 surface or degree 1 surface, then you find infinitely many lines. And for example, for degree 1, this is just clear because, I mean, degree 1 is a linear surface. And so a linear surface in P3 is isomorphic to P2, but P2 has infinitely many lines in it. You can move the line around wherever you want. And so at least in that case, we can just check it, that there's infinitely many lines. For degree 3, we have just compute, I mean, this was the entire chapter here. We have seen its finite number, namely 27. And then if you have degree greater than 3, then you have more equations than variables. Of course, this could potentially go right. I mean, sometimes you have equations are redundant, but in this case, you expect that the equations are basically independent. And so a general degree D surface X will have no lines at all. So the counting problem is pretty boring. And so this dimension argument explains why we exactly look at a cubic surface and count the number of lines, because that's exactly where the number of variables and number of equations matches up. Okay, so this was the treatment of these 27 lines, and then in the remaining part, we're going to look more at this surface X itself and find out whether we can characterize how we actually get the surface X. Okay, so this is in the next video.